hold paramount the safety, health, and welfare of the public. This comes in at the end of the 1800s when some bridges fell down in the UK and in Canada, and they realized that we need to do a better job. It's a great canon, and I wish more people knew it, especially engineering professors. Anyway, so we talk a lot about creativity and innovation. So creativity is thinking of new and useful ideas, and innovation is making them viable. And I'll try to work or maintain this theme here as we go along. First, a word about engineering design. Lots of people think that the drawings that we use are the designs. They're just one representation of the design. And the interesting thing for me in looking at design theory is, where do these come from? How do we get these ideas? And how do we develop them into such sometimes intricate drawings? So engineering design, it's conceiving, planning, comparing, selecting components and systems. And so engineers create value by thinking. As I point out to my students, we don't really have to do anything. We just sit and think, and then we need to provide some representation of what we've been thinking about, I guess, especially if we want to get paid. And so thinking about thought, and Descartes, je pense donc je suis. I think, therefore I am. And he comes up with Cartesian coordinates, and he did quite a bit of good thinking. But then thinking about thinking, metacognition. And this is essentially what design theory is. Thinking about, how did we come up with this? And that goes back even further to Aristotle. So I kind of think of design theory as trying to guess where ideas come from, and then figure out how to make them viable, how to make them work, how to make good innovations. And as I mentioned, too few engineers are familiar with the first canon of ethics, or with design theories, interestingly enough, since that's what it is that engineers do. So engineering design starts with needs. And it became clear to me, so I coached and have done a bunch of athletics. And it became clear to me that we were having way too many injuries when I looked at this book that came out in 2008, Warrior Girls. And the chance of tearing your ACL, if you're a high school girl athlete as opposed to a boy, is 7 times greater doing similar sports like soccer. And there's a lot of questions about why, and nobody really knows, but the idea was, let's try to find a solution to this. And here's some statistics on these, and they're alarming. I think it's like every time a high school girl basketball player steps on or every 2,000 times a high school girl basketball player steps on the court, she'll tear her ACL once. And so that means most high school girl basketball teams are going to have at least one ACL tear every couple of years. And when you talk to people, that seems to bear that out pretty well. So how do these happen? And I start thinking about it as an engineer, and many of the injuries occur from loads that are transmitted from the floor or the field through the shoe to the person. And that's where we have an opportunity to do something in the shoe. But so what else might we do? And so what's going on now? The exercises and trying to strengthen your knee to prevent injuries are a great idea. They work, but you need to do the exercises, and they're not absolute. Ankle supports, and some of these expensive shoes have got all kinds of ankle supports built in, and that's nice, and that can help the ankle, and so can taping. But the problem is that as we support the ankle, we increase the loads on the knee. one of the things the ankle does is absorb loads before they get up to the knee. And so it's been noticed that, if you tape the ankles, and sometimes you do it as a prevention to keep the ankle from getting hurt, you tend to have more knee injuries. And we see a similar thing in skiing when the ski boots started to get higher now about 50 years ago. But so design theory, I'm going to talk mostly about a different kind, but I want to mention this. These three professors from the École des Mines, or Mines, Paris Tech, were teaching innovation and design to industry, and they developed this, and I think it's a nice theory. And they talk about dividing sort of into two spaces the engineering design problem. One is the concept space. So we get some idea as a concept, but then to be able to execute this, we need some knowledge. And sometimes that knowledge already exists, and all we have to do is find it. And sometimes we need to develop it. And so ideas may have sort of children, and we may need other knowledge to develop this, and that knowledge may lead to something else and some other things, and you get the picture. But the main idea is that we have concepts that we would like to use to make products or processes or systems that are going to be useful, and we need some sort of knowledge to turn this into an innovation and make it viable. So we ask sometimes, well, where did that concept come from? And in the case of what we are doing on the shoes, it comes from ski bindings. And I had the good fortune to work with some of these guys at the University of Vermont, Bob Johnson, who's an orthopod, he's now retired, and Carl Ettlinger, who's an engineer, and then their associate, Jake Shealy, who's at RIT in Rochester. And they've been studying injuries at Sugarbush North when it was still Glen Ellen years and years ago. And this is an interesting trend here. So this is tibia fractures. And starting off, tibia fractures were not far off that 1 out of 2,000 days. And there were a lot of tibia fractures. Release bindings had been invented actually in the late 30s, but there was problems with getting them to operate properly. And finally, they got the friction out and they got everything working. And you can see a dramatic improvement. So this is days between injury on the left and then the ski season on the bottom. And so now these tibia fractures are very rare and often associated with some clear malfunction in the equipment. So my thought was, could we use those? I should go back to that. Can we use the same concept? Because the binding essentially is intercepting these loads and trying to keep from transmitting potentially injurious loads to the tibia. And it works very well for the tibia. It doesn't work very well at all for the ACL, and that's the topic of another lecture sometime if you want. So the theory that really captured me when I was a graduate student was Nam Su. He came to the University of Vermont and gave a talk. So Nam was a professor at MIT at the time. He went on to be at the National Science Foundation in charge of engineering and chair of the mechanical engineering department at MIT, and then president of KAIST, which you may not have heard of. It's the #2 engineering school now in Asia, Korean Advanced Institute for Science and Technology. And Nam was originally from Korea. His father was a professor at Harvard, and he got stuck in Korea during the war just before he was going to join his father. Anyway, he goes to high school in Cambridge, Mass, and then to MIT, and then Carnegie Mellon, and then comes back to MIT to teach. Anyway, he's now retired, lives in Massachusetts. His first honorary doctorate out of 8 or so is from WPI. And the axioms he discovered in the 70s. And he was looking for commonalities in good designs. He started off with this premise that there should be self-consistent axioms that apply to all good designs. There should be certain things that we would use to get the best solution for all design problems. An interesting position, and many people disagree with it. They think, no, it's just creativity and we got to think outside the box and ideas just come to us. And so let's take a look at the axioms. Now, these are two things that he said are common to all good engineering designs. One is maintaining the independence of the functional elements. So function is important, and we're going to develop this a little bit. So if they're independent, they're adjustable and controllable. We avoid unintended consequences, and this drives us to modularity in design. The second is minimizing the information content. So sort of too much information, and we can see poor Homer Simpson here is suffering from too much information. Don't confuse information and knowledge. Information content is about the probability of success. And so if there's too many instructions, for example, to accomplish some task, the chance of achieving or successfully accomplishing that task goes down as the number of instructions go up. So the chances are somebody's going to misinterpret one or forget one and not be able to make it work. So the message here is to avoid unnecessary complexity. Lots of designs have to be intricate because they're doing so many things. And this leads us to robust designs. Now, a lot of people say, oh, those are simple. It's just common sense. Well, if it's common sense, then why aren't more people aware of it and using it? And I like this philosopher, Karl Popper, who noted that why simpler is better. Simpler things tell us more, their empirical content is greater, and they're easier to test. So in order to apply the axioms, we need some sort of structure. Just as if we want to apply Newton's laws, we need like a free body diagram. We need some sort of analogy, free body diagram analogy in design. So we like to divide things into spaces, as we could already see from the CK theory. And so Nam came up with these design spaces, which are quite useful and appropriate. So we start with the customer needs, just as we were looking at the shoe, and we need to do something about all these injuries. Then from those, we derive functional requirements. This is what it does, and these must satisfy the customer needs. Then we go on to design parameters in the physical space. This is what it looks like. The design parameters have to fulfill the functional requirements. And then we could also talk about the processes, the process variables, so that we can manufacture things. But we'll save that for another day. And mostly what we want to focus on now are the functional and physical spaces, although we'll get on to customer needs too in a bit more detail towards the end. Design thinking. We hear about this a lot, and I don't know what this really means when most people use it. But I like to go back to form follows function. So this American architect, and here's one of the buildings he developed at the end of the 1800s. Quite a departure from conventional architecture, which was more innate and had a lot of aesthetics built into it. This is, let's get the function. Axiomatic design too is form follows function. So we develop the functions first, the functional requirements based on the customer needs, and then select the form or the design parameters. So let's get back to our problem with the injuries. So there is a need to reduce the injuries, and the cost of these is something like $10 billion a year for high school and college in the United States, almost enough to pay for a pandemic. All right, so we've got the shoe is getting loaded from the movements of the person, and we try to work for better and better traction on the shoes so we get better and better performance. Well, we don't want to mess up the performance, but we don't want to mess up people's knees either. So let's control the load transmission through the shoes so that without diminishing the performance, we can avoid injuries. So our first FR and the top level is always FR0. So FR0, let's absorb somehow these potentially injurious loads to the knee and the ankle in the shoe. And so what we turn to is a special sort of split sole, so that we've got the bottom part of the sole is for the interface with the court or the field. And the next part is to hold the shoe upper and the foot. And in between the two, we're going to use tunable springs. And the constraint that we have on this is to maintain performance. Through excessive experience in athletics, I know that nobody's going to use a shoe, even if their knee is a lot safer, if it diminishes their performance. Okay, so a little bit more on the structure. So we have these different domains, which is a kind of horizontal decomposition of the design problem. And now we're going to decompose it in hierarchical fashion from abstract to detailed in these parallel vertical hierarchies between functional and physical. So what we're looking at here is a series essentially of parents and children as we decompose, say, FR1 into its three parts, FR 1.1, 1.2, 1.3. And in parallel, we have the same sort of decomposition in the physical space, but this is describing the functions, the functional space, and this is describing the physical solution to the design problem. And so there are the children for FR1 and DP1, for example. So we need some process also for creating this or doing this decomposition. And because we're going function first and then physical, and we'll talk about that more in a moment, it's called zigzagging. So first we get the function, then the physical, then we go down to a level of detail and do the next level, function to physical, and so on. And we keep decomposing like this until the solution is obvious. So we can sort of look at the decomposition like this, and it's not much different than cutting up a pizza or something that you're going to eat. You can't get the whole pizza in your mouth at one time, so you split it up somehow, and then you split it up again when you bite off pieces of it. So that's kind of what we're doing with the design problem. And this decomposition process is key to doing any kind of problem. And I think it should be something that is taught from a very basic level, but we don't. But sometime we should. Now, there's lots of rules that help us in the decomposition. Lots. There's a few that are good to remember. One is when we're talking about functions, they start with verbs and they're stated in the imperative. So it's a command. So you need to do something, accomplish something, provide something. And we would like the minimum number that we need to satisfy the parent or satisfy at the top level the customer needs. So we want to make sure we think of everything. So the decomposition should be collectively exhaustive. When we take all the FRs together, we should have the problem solved at each level of detail. And at each level of detail, the FRs should be mutually exclusive, so there's no overlap or redundancy. So we have a good, clean, full decomposition, but no more than we need. And the little mnemonic is C, me, min, collectively exhaustive, mutually exclusive, minimum number. We also, in the decomposition, another way of thinking of it is we want to somehow be able to combine all the children to equal the parent, exactly. No more, no less. This would mean we have a good decomposition. Now, I have a summation here indicated, that the sum of the children equal the parent, but it's any kind of combination, doesn't have to be a summation. So concept. So going back to the concept knowledge from CK theory, from our friends at the École de Mines. So split soles are going to be embedded with tunable springs that will control the ground reaction forces. So this is going to mitigate the loads on the knee and the ankle, even with ankle supported taping. So we can avoid putting the knee at more risk by when we save the ankle. So we started on this problem not long after that book came out with a team of undergraduates working on their MQP, major qualifying project, which is what WPI calls the senior thesis in engineering. So in undergrad, for the undergrads. And these three did a great job. And so we filed for a patent. And so here's a little bit more on the decomposition. So functions first. We want to absorb the loads in a horizontal plane, and we want to absorb the loads in a vertical plane. Because we look at videos of the injury, and lots of times somebody's coming down from blocking a shot or something and trying to make a cut, and that's when they injure their knee. So the physical solution is these sliding horizontal soles with tunable springs. And so we have these horizontally, and we also have a spring system vertically under the heel. So so the idea is we should be able to absorb in both directions, or both senses, horizontal and vertical. So here are some frames from a video of the prototype that we made for the MQP. And so this is a force plate down here, that's gray stuff on the bottom. And then here's the shoe. And we literally took a bandsaw, cut the sole off, and then put our spring system in. And then we had to hold it back together. And this is an exercise band that got stitched onto the shoe to hold the whole thing together. And you can actually see the shoe deforming here as this person makes a cut. And you could measure the difference in the forces between that and a normal shoe. So we knew we were on the right track. But this got put on hold for a few years. We tried to sell it to shoe companies. And the established companies seem to be a little bit risk adverse when it comes to investment in new technology. Not just the shoe companies, most of the big companies are. We could speculate on why, but anyway, it happens. So our first attempt at a spring system was a kind of cantilever beam. Now, a cantilever beam is one that sticks out from something and then can get pushed over like this. And that's what all these 120 things are around here. And so these would get pushed over in different fashions. This is a drawing out of the patent, and it's terrible. It shows a sharp corner there that should be rounded. This thing's supposed to be bending over. And we knew that wasn't going to work exactly what we wanted to do, so we tried all kinds of designs. Whoops. Let me go back here. And this one, we start to get into what we ended up calling a goat's head, quite conveniently, because a goat is, after all, WPI's mascot, and it kind of looks like two curly horns on a goat's head. And so this one we kind of get to, it's an evolution from this thing, where we have the spring sort of on a curve like that, and the upper part of the shoe coming in like this. But here's the problem, and we needed some new knowledge. Conventional springs are linear. This goes back to Hooke's law. Hooke was, I've forgotten what century, but it was years ago. He discovered when you pull on most things, they stretch a little bit in a linear fashion. So this is a coil spring, but it could be any kind of spring, or it could be just a wire, and you put some weight on it, and for a while it will deform what we call elastically, and then spring back. And then either the spring stretches all the way or bottoms out, and the loads start to go up. So if we think about this in terms of our problem here of, let's say, reducing the risk of injury and still being able to do ordinary play, So let's take a look at a plot of the load here. So this could be a force or a twist, and the displacement, which could be linear or angular. But so if we look at the load levels, there's a certain level that we need for most ordinary play. And then above that, there's some load where we start to have some significant risk of injury. We know they're oriented like this because most of the time we go out and play without getting hurt. Otherwise, we wouldn't do it. So if we look at a linear spring, a Hooke's law kind of spring, so this is the load is equal to some constant times the displacement, and it just goes up like this. And this would be all kinds of springs like on a pogo stick. I don't necessarily want a bouncy kind of feel. And so like ski bindings, preload the spring so that it doesn't start displacing until I get up to some pre-adjusted load, say L0. And then I'd like to kind of flatten that out so I've got a longer time before I start risking injury. And if the ski binding's working properly, it'll release somewhere in this window before we actually get hurt. Now, what we would like more than this would be to have a spring that goes up and then flattens out somehow. So we would like a nonlinear spring, because this is linear where it just keeps going up. So this would provide us better protection. And if we can double the displacement, this comes out of a kind of work energy formulation for those of you who are taking physics and mechanics. And so if we can increase the displacement, say S, by a factor of 2, we can reduce the forces that are necessary to in the energy let's see. If we double the displacement, we can have the forces essentially, and provide more protection. So what's happening is some initial linear kind of displacement, perhaps, or stiff load, so that we can make the different maneuvers we want to when we're playing. And then we want to get into a protection mode where we supply, we're able to keep loading at a safe sort of load so that we don't have a release. If you had a release, you say, uh-oh, we're approaching a dangerous thing here. It would be like you stepped on a banana peel and you'd kind of skid out. So what we really want is something that'll allow us to maintain an approximately constant load at a safe level, and then absorb as much as we can, keeping the forces low, and then recover when we pick up the foot. So whenever what we're doing is over, and it will get over because we can only extend our legs so far, and it'll recover before the next step. And we may not even know that the shoe has saved our ACL. Actually, we prefer that we didn't really know, so that we can go on playing without any interruption. So we can look at the work here that's absorbed and come up with, if we can double the displacement, we cut the force in half. And actually with this kind of shoe, since nobody's paid any attention in shoes to horizontal displacements like this, we can do better than doubling it. We can also look at an impulse momentum kind of formulation. And so this is integral of force times time, and we're changing momentum when we change direction. So if we use some sort of tunable spring system, we can reduce the load, as I've shown, and we give a little bit more time. The times are still milliseconds, but this can be enough time perhaps to respond, turn your muscles on, and save yourself from injury. So same impulse momentum with the tunable springs, lower force, longer time. So let's take a look at our first branch, and we need to find some sort of system for absorbing the loads and to decompose this. So we'll decompose it sort of in a way that Descartes would like, fore, aft, medial, lateral, and then we're thinking, all right, forefoot, heel, and also we have different diagonal loads, and then we've got rotational kinds of loads. So we're trying to be collectively exhaustive for all the loads that we have to think of, and then and mutually exclusive because these all have special directions. It turns out that this is tough to achieve absolutely, but it isn't tough to be better than what currently exists because nobody's trying this. So anyway, here are the different tunable spring systems that we're looking at. And here they are physically integrated into one shoe, and they're all kind of hidden here. And so the challenge is to make this spring system small enough and in the right kind of form so that you can fit it in the sole of the shoe. So here's an example from a couple of years ago, how we were doing it. And one of the things that we want to be able to do in a good design representation is to be able to point to, whoops, a little bit too fast, be able to point to all the physical aspects and figure out what the design intent was. In other words, what function are they fulfilling? And this is very often, most often, not recorded with the design. So, and this causes problems. We could build another Saturn V moon rocket. We have all the plans. We can't change it because we don't know what the design intent is, and we would have to somehow reason that out. Well, it turns out these nonlinear springs are not very common, and so we needed some new knowledge. And this is something I had been thinking about for years, literally, because this is what I would really like to put in a ski binding. And I got to start working on ski bindings at the University of Vermont in about 1980. This configuration, so the spring is the elastic material, the red. We call it the goat's head. Maybe you can see why. And it's a tunable spring. And what we're doing, the only part that we're stretching is this little bit right here. So we figured out essentially how to break Hooke's law. And Hooke's embodiment, we're taking the whole spring and stretching it at once. And in this configuration, whoops, we are just deforming a little bit right here where it goes from curved to straight. This part of the spring doesn't deform until it gets right to this deformation zone here. And then after it goes through that deformation zone, it just stays deformed. So this is the only place where we're doing work on the spring. And so we have this actuator that pushes down, and this can give us that nonlinear behavior that we're looking for, and we can make it tunable. Now, the other thing we need to do is have it work in all directions independently of the others. And so this is a little device, an early embodiment of this. Later we figured out this has got to be circular so it can rotate. But this little slot here allows that actuator in the middle of the goat's head not to react, not to be moved fore and aft if this is the medial lateral actuator. And all right, so here you can see some physical integration work that we did. And here is, you can see the little parts of the goat's head, and here they are over here too in the photograph. We started making much better progress on this when we bought our own 3D printers and sort of had control over them. WPI has lots, but we needed some dedicated in the lab, and so we got those. And here we can see in the heel, here's the vertical goat's head, and those act just in one direction in this embodiment, whereas these two here are going to be turned, and these should be the fore aft ones in this point, and these should be medial lateral and toe and heel, but somebody got that wrong. All right, so in any event, we're looking for other ways of doing it. We need other solutions, and this is what we call the actuator in the elastic field. And so what we have is an elastic field with a stiffer kind of actuator in it. And so it's sort of resting like this and sitting in a little pocket. And then when it gets displaced, it compresses the elastic field a little bit here, and the elastic storing force. So this is kind of like pinching a watermelon seed and getting it to move. So it'll react to the applied load. And depending upon the shape of this and the way we do this, we can get different kinds of responses. It could be a foam or a brush, but some kind of elastic field that the activator moves out into. So when we want to take a look, especially to see if things are coupled, we can make a matrix like this. So up here we've got the physical solutions, the design parameters, and down here we've got the functions. And the X's indicate that there is an interaction. Now the diagonal X's are the ones that we really want, and the off diagonal X's are the ones that are causing some coupling that we know we're going to have to deal with because they're giving us some problems with axiom 1. And because we don't have separate springs for diagonal and rotational, we're having some interactions here with the 4 aft springs and the medial lateral, because these have to do sort of double duty so that we don't have to build up more layers. And so we have a constraint where we need to keep the thickness of the sole reasonable, and we can't put in a separate layer for doing diagonal and a separate layer for doing rotational. So that's the origin of that coupling. So as I was saying, twice the displacement, we get half the force and twice the time, and we can do more than twice. And so conventional, and then here's the prototype on the force plate. Yeah, we had to come up with some other solutions than these cantilever beams around the outside, because unfortunately we're using an orange band here, and the investors were saying, we're mentioning some similarity with Ronald McDonald's shoes, which was obviously not going to be a good selling point. And we were so fortunate, and I've got to mention sports engineering, that was in the lead slide, and I forgot to do it there, and I forgot to point out the knee. But Sports Engineering Inc. is a startup that our investor began to support this project, and we've had good fortune to have wonderful investors who are very patient as we think of better ways of doing things, integrate them in the shoe, and improve the final product. And they're understanding very well that this takes time, and nobody had a tunable spring before. Anyway, so there we've seen that, I think. So here's some of the integration steps that we have putting everything together. And here's some points here that we could use. We can, we've also got a patent now that we've applied for on skates. Actually, we have an existing one on figure skates to absorb loads in the heel. Because if you miss your jump and land on your heel and don't absorb it well with your knee and your ankle, you can get a severe bruise that'll keep you off the ice for a while. The investor actually came to WPI. His investment strategy is looking for undervalued intellectual property at universities. So schools are not that apt at developing their intellectual property. And so he came and he'd seen our patents on ski bindings. We've got a number here where we're looking at avoiding inadvertent release and ACL injuries. So this is actually Lindsey Vonn tearing her ACL yet again before she finally had to retire. And this comes about as these stiffer boots start to penetrate the market. And here we see a decrease in the mean days between injuries for ACL injuries. And they're in skiing, they're at about the same rate now as for high school girls basketball, about 1 in 2,000. All right, so there we have some design activity and some solutions that we've worked out and how we put this together. Let's think about what we did. Let's think about thinking for a moment. So design, philosophy or a science? So, and we're using the term science here in the sense of a scientific discipline is one that has a few sort of simple, self-consistent laws or axioms that we can apply to a wide variety of problems, like Newtonian mechanics. And it's interesting in this development here that I read about in the New Yorker, I recognize that what I'm doing is sometimes So this is thought, as Adam Kirst describes it here, before it's really had a chance to solidify and form a scientific discipline. So if we look at sort of natural philosophy and what existed really before Newton started to transform the way we think about the world. So are Sue's axioms solidifying a philosophy of design and making this engineering design a scientific discipline? I would say yes, but I leave the question open. Let's consider customer needs. Now, the design problems are starting with a need. And Henry Ford is supposed to have said, if I'd asked people what they wanted, they would have said faster horses. So we have to be careful sometimes how we interpret needs. And we have to make sure that we haven't limited our solution space. So if Henry Ford had just asked people what they needed, he would have been probably an unknown horse breeder in Michigan. And as it was, he realized the problem, the fundamental need is transportation. And how can we supply this in a better way? And it's interesting how much time it took him to develop. Well, the Model T was not where he started in the alphabet. Anyway, okay, so from the customer needs, we need to formulate what our functions are. So we need to understand these well. And here's a little hint. When you think you've got a need, ask why. And there was a thing that the Japanese developed in manufacturing and solving problems. Ask why 5 times. I'm not sure why it has to be 5. And sometimes 1 or 2 times will do it. And you think, I'm to my fundamental need now. And when you get to the fundamental need, you've got more possibilities for solution. Anyway, I'd like to recognize our design team, and WPI is a great place to do this work. We've got lots of bright and energetic undergraduates that we can work with, as well as graduate students, and we've been fortunate to have some visitors from schools in France as well. And so here we are working and enjoying some spaghetti at some point. Very quickly, Nam has written 3 books that are very good on design. This was the first one from 1990 that covers the basics. It's a tough read, but I recommend it. I recommend all of these. Complexity, he gets into some interesting issues of complexity in design. And one of the things he talks about in that book is the need for periodic reinitialization, which I'll mention again in just a second. But as we're wrapping it up, let's design a future for a planet with a future. Let's try to leave the Earth better than we found it. And let's keep the first canon of ethics in mind. Hold paramount the safety, health, and welfare of the public. And occasionally we need this periodic renewal or reinitialization. Things get messed up enough and we got to kind of take a breath and start over again. And that's one of the things Nam talks about in his complexity book. And this little thing by Auden here, W.H. Auden, this little poem is kind of about reinitialization. And here we can see actually it's my son and who is uncle to my grandson here. And in the background, you can see the sap lines in the sugar bush in Vermont. But so we're going through a kind of periodic we hope it's not periodic, but a reinitialization here. I guess it's periodic. I guess we went through this about 100 years ago. Anyway, so Auden, he's an Anglo-American poet, and he's known for saying, "We are all here on earth to help the others. What on earth the others are here for, I don't know." And then another little one that I like about my profession. There are some days when I think I miss my calling. I should have been an anesthesiologist. Anyway, I look out and I see students asleep. So a professor is one who talks in someone else's sleep. So thank you for your attention. And one of my good friends caught me at a meeting in Sweden and suffering from jet lag.
Well, thank you very much. We'll take some questions now, but it really is, you know, I can't say that I understand every single last bit of minutia there, but the way that an engineer looks at the world, and I also kind of see where you get that picking up the trash wherever you go comes from in those last slides there, and I appreciate you for that. So I would love to take questions. I will remind or let people know that you are being recorded, just because I think you're supposed to do that in Massachusetts. But any questions, and all questions are welcome. If you want to raise their hand or do it in the chat, I can read chat questions as well. Let me see if I can see everyone at once here. I don't think I can see everyone at once, but or you can just unblock your microphone and have at it.
And I should have given you my email address. If you have some questions later, my email is very simple, brown@wpi.edu. If you forget it, you can go just Google me at WPI. If you just Google Chris Brown, you'll probably get somebody else.
Questions? None.
I put one in the chat there. Mine was
Okay,
just,
sorry.
thank you
Yeah.
for your talk. It was very interesting. Just curious how closely you work as an engineer with the other stakeholders, like the trainers, athletic trainers, and athletes, and anatomy, you know, biology people, to look at not just the design but also the kind of the biomechanical side of everything.
Well, we probably don't do enough. The president now, the new president of Sports Engineering Inc., is somebody who's been in the shoe business for a long time, and he's a shoe consultant all over the world, and he's been encouraging us to do more of this. I had the good fortune to work. Actually, I took care and prevention of athletic injuries and did a lot of taping myself and a lot of athletic experience. Right now, I think the problem, the immediate problem, is to get all of this integrated. And then as we start adjusting things and figuring out what we really want for load displacement curves, we're trying to do that. That would be the point at which we need to get some more input. But yeah, we should be doing more of that. And if anybody here knows somebody or knows something about this, I would be glad to chat with you.
I had a question. How close are you to commercialization? I mean, you see the prototypes there. Are there any shoes? Are they being manufactured right now?
No, and we're still working on the prototype.
Mm-hmm.
And we would like to have equations that relate the design parameters, like the thickness of the spring and that force displacement curve, and be able to adjust that. There's a lot of uses for the shoe, and there's a lot of development that still needs to be done. How do we know what load somebody needs? This is a problem in skiing too. How do we adjust the ski bindings? So there's still a lot to learn. And our goal is not to manufacture the shoes ourselves, but to sell the technology to shoe manufacturers. I'd also like to see, and we're working on several different embodiments, and I haven't shown you all of them, obviously. I would like to have some very affordable ones so that any kid shooting baskets in Roxbury can afford the shoes, and have some that are very sophisticated, so the new quarterback for the Patriots can also have some that will be tuned to him.
There's a question in the text. It says, would you share references to a technical paper that describes your designs for impact absorbing footwear? I see the patent, but others.
Yeah, we haven't done much on publications, and we're doing a completely different kind of technology. So vertical absorption is all people are really worried about, not horizontal in conventional shoe design. and everybody's doing it with foam or gel or sometimes little air pockets. And so that's completely different. One of the problems with the foam is it can compress about halfway and it bottoms out. And it works more like a linear spring. Although some of the foams have got some of the characteristics we'd like in a tunable spring. But so in half the space, it bottoms out. And our design will get rid of most of the foam, and then we can use all of that space, or much more of that space, for absorbing the load. For references, though, I don't have any good articles, but there's a couple of books. Hang on. So these are kind of classics, and this guy Nig is out in Canada, and I think his children have somewhat taken over his consulting. But and so biomechanics of sports shoes, and this is loaded with references. So if you want some, I suggest getting this book. And then there's an older one that also has a lot in it as well. So, and if you didn't get those when I flashed them on the screen, email me and I can send you the full citation. One of the interesting things, though, and I hope I made that point well, the only, we're all familiar with nonlinear springs, although people hardly ever mention them. So your vacuum cleaner cord, if it's got an automatic rewind on it, is probably a kind of nonlinear constant force spring, but it's a large displacement, small force. Same with a tape measure when you pull it out. Large displacement, small force. And we need to do larger force, small displacement, because we only need to pick up a few millimeters to put a big dent in the maximum force.
I'm gonna put the survey in the chat box. So when we're through here, it will literally take you maybe 2 minutes. I think there's 3 questions on it, just to get a sense of feedback. But other questions? It was very comprehensive.
There's, if you go talking with engineers, like most of them will not have heard, unfortunately, of the first canon of engineering ethics. We don't do a good job of teaching that, nor will they have heard of axiomatic design. So I'm giving you some different insights here. There's a few of us that teach axiomatic design at WPI, and the other 2, I think, did their doctorate with me. So
maybe we should ask our WPI grad if she knew about axiomatic design before today.
So who went to WPI?
That was me, 2000 and 2004. So I am also mechanical. So I'm sure I was in one of your classes at some point because I remember that part. Yeah.
Good. It worked.
Yep.
One of my observations is that the spring, the goat's head spring, which is really fascinating mechanism, it resembles a lot, of course, the goat from WPI, but our mascot is the hilltopper, which is a sheep with the horns and looks very much like that as well. So it could be a hilltopper.
Yeah, I think the sheep, more sheep have got those curly horns, and WPI.
The goats are
Yeah, mascot is the straight ones, but we couldn't resist when we saw how this was turning out. We went with the goat.
Well, if there's nothing else, we can close it up. And again, if you would just take a moment to click on the link, the form, and give us a little bit of feedback on today's presentation, we appreciate your time. And again, a little round of applause for Chris for coming out and sharing with us.
Well, thank you very much. Thanks for the opportunity to talk to you. And as I said, I'll be happy to follow up with anybody. Just send me an email.
And if anyone wants to hang on for a minute or two and speak a little bit more, we could do that as well.
Yeah, I'm happy. I've got, at 5 o'clock, I've got to do a Zoom class.
Yeah, he told me a story about how he was supposed to be in South Africa, and then they told him, I should let him tell a story, but they told him that he thought it'd be a 6-hour course that he was preparing for. So he prepared all the stuff. And then yesterday or 2 days ago, they called up and said, no, it's just an hour and a half. So he's been through the ringer today already.
Yeah, well, it's hard to sometimes cut down from 5 hours to 100 minutes. But also I thought that I wasn't sure that they were going to do it, and I wasn't hearing from them.
Mm-hmm.
And I guess they've been scrambling like crazy. So yeah, I Zoomed to a meeting in South Africa that was attended by people from all over the world this morning for a little over an hour and a half. So the Zoom is great. So now I'm Zooming all over Worcester. But yeah, I'd be happy to hang out.
Thank you.
You're welcome. My goodness, it's just like a class.
Yeah.
Don't get in the way when the class is over.
Yeah. Knock you down. Jamie, did you have a question? No, he's not. That's all right. He was the trainer.
Oh.
Yeah. I thought he might actually have a question, but yeah. Well, very good. Thank you. It's in the books now. I can stop the recording.